We continue now with the module manufacturers, and the first company that will talk is LONGi. We have with us Jason Yan, who is the Senior Product Marketing Manager at LONGi. He has 6 years of PV R&D department experience with new materials and product development, and is working now at LONGi as a Senior Product Marketing Manager. And he will talk about the analysis on the value of very high power modules based on levelized cost of energy. Jason, the floor is yours. Good to have you again.
All right, thanks, Michael, for a kind introduction. So first of all, I think I need to share my screen. So hello everyone, this is Jason Yan from LONGi. So today my topic is about analysis on the value of very high power module based on LCOE. So first of all, I will introduce the significance of developing very high power module. Basically, when you are in the module manufacturing business, it's like you are in the race to facilitate our customer to attain lowest LCOE. So we have been in this race, I think, from 10 to 20 years. So improving high power model is an important approach for getting a lower LCOE. If we look at the equation of LCOE, we can find that if we increase the module power, that means we can reduce the both cost and the module cost. However, in the same time, we need to ensure the stability of energy yield and system and module reliability. So the core of reducing the LCOE for power plants is to consider comprehensively the reliability of the whole system of modules and stability of energy yield. Therefore, it's not correct that the larger module size, the better. It's significant for modules to resist extreme weather conditions such as storm, hurricane, hail, etc. When we look at how to increase the module power, we can have a variety of approaches. Firstly, we can increase the module size. Actually, in 2018, the industry began to think about the increasing the power by increasing the size of the module. For example, we can increase the cell area, or we can increase the cell number. And secondly, we can adopt the module efficiency improvement technology, such as half-cut, MBB, and some new materials such as coated glass and white EV. So as the expert mentioned before, so half-cut and the MBB technology have been dominant for nowadays the module technology. And lastly, we can also use the high efficiency cell. So for nowadays, prox cell is still most cost-effective cell technology. Also, we can increase the module power by increasing the module size. We need to be very cautious by designing the module size, since if the module size is too big, it will cause a significant increase in the reliability risk. So we need to analysis on the boundary conditions of larger size wafer and modules for finding an optimal module size. First issue is that does it make any sense to unify PV and semiconductor silicon wafer? So when we look at the PV industry, when the wafer and the cell become larger, the design of PV module and the system will change greatly. However, cell cost is only accounts for 7% of PV system cost. So the cell manufacturing cost is not the key factor of the industry chain innovation. Different from the PV industry, when we look at the semiconductor silicon wafer, when the silicon chip becomes larger, we can save a lot of manufacturing cost. So we cannot simply use a semiconductor chip wafer for the PV industry. And then we need to consider comprehensively different factors from model manufacturing process to the model deployment process, such as model installation, model transportation, and system capability and model reliability. For considering all these factors, we can design our optimal model size. In terms of the shipping issue, so landscape package, we know that is widely used and verified for many years and mature and reliable. And 182 millimeters wafer size is optimal size derived from the 400 high square inch container, which can deliver high value to customer. And the following is just a simple equation which calculates the wafer size. If the wafer size is bigger than 182, that means we need to change the package model to a tiled or the portrait package. So in the right-hand side figure, we can see if we change the package to tiled or portrait model, the following kinetic energy, shock energy, and frame stress will all increase. In this case, and which will increase the risk of micro crack and breakage and falling. And furthermore, when the models in the container is shipped to the field, and we need to unpack the models. And on one hand, it is difficult to unpack the models with portrait package. You can see from the left-hand side figure is the height of the package is too high, and the dumping kinetic energy will increase obviously. So this will increase the risk of accident. And another issue is that if we want to ensure the system stable, we need to add an anti-falling bracket beside the models. That means we need to, for example, at least 200 kilograms counterweight is needed when the tight angle of model is 85 degrees. And furthermore, when the wind gradient is 5, so the number of model is less than 9, the bracket will be blown down by wind after calculation. So that means if we use the portrait package, there is a lot of limitation and will have an increase in risk of accident. As I think as George mentioned that the model reliability, we also do the analysis on model reliability. First issue is about the mechanical load. So for example, if the model is under static load, the increase of the model size will let it increase the frame stress. So in the middle figure, we can see if the model size is, the model width is 1.1 meters and the model length is about 2.2 meters, it will be in the safe zone, and the frame stress will be around, I think it's below 240 megapascal. And if the model width and model length is bigger than that, so the frame stress will be close to 255 megapascal. Actually, the 255 megapascal is a maximum tensile stress of the frame. So that will cause the breakage of the frame. And I think the 182 model is under the safe zone. Another way is that under dynamic load, for example, is 100 Pascal dynamic load. which is I think is equal to about 36 meters wind speed. So the oversized model, in the right-hand side figure, we can see if the model size is bigger than 2.8 square meters, the shear stress will be higher, and it will reach the red zone, and thus will cause that increase the risk of retiring the mounting hole. And also for the mechanical loading, actually we did analysis on the different waste class with the increase of the model waste, and the maximum deformation actually will increase from 1.13 meters to 1.3 meters. The deformation will increase about 40%. So in one hand, the large deformation will cause the power degradation about 3% higher, and on the other hand, the risk of glass breakage will increase. And also for Junction Box, as we know, when we look at the history trend of the Junction Box, we can see we always use a higher Junction Box current, which is the current is higher than the theoretical current, and all of this from the 156.75 model to the 182. So the safety margin is about over 10%. And for the 210 bifacial model, if we use the 25 amps Junction Box, that means not enough. So we need to use at least 30 amps Junction Box. And normally, 2 parallel diodes were used in the 30 amps Junction Box, and that will increase the failure rates. And besides, the uneven of the 2 parallel diodes will increase the risk of failure caused by uneven current. And also for the manual handling, we all know that the motor width is derived from the natural expansion width of the human arms. So the too wide of the motor will cause inconvenience to the installation. And according to the manual handling and work brief guide published by HSE, we can see the maximum weight of 2-person carrying should be below 35 kilograms. So when we look at the figure in the left-hand side, for the 210 millimeters motors, if the type is 60 cells and 66 cells, the motor weight will be larger than 35 kilograms. That will increase the risk of accident significantly. And so based on this above the analysis on the boundary conditions, we can see if we use the model based on M10 182 size, there are no unsolvable obstacles in other aspects, both from the model mounting and system compatibility and reliability and the feasibility cost. All of this is good for the M10 models. So secondly, I will introduce the analysis on the both cost. I will introduce the 2 reasons why larger model saving the rack and the foundation cost. So first of all, the increasing of the rack length will save the number of foundation. We can see in the left-hand figure, if the rack length is double than the top one, that means we can just use 5 pile foundation. And if the rack length is short, we need to use 6 pile foundation. That means our higher the longer rack length will save at least 1 pile foundation. And another reason is that the increasing of the rack width will increase the supporting power for each foundation. And in this way, it will dilute the amount of steel used for each rack. And we did analysis on the rack. So For the utility scale power plants, it can save rack and foundation costs by using larger rackers. And considering the thermal expansion and the contraction, the length of racker is limited to about 120 meters. So both 182 and 210 models can save the cost using larger rackers. And we can see the calculation results as follows. And for different installation, like a landscape and portrait, we can get the rack cost of the 182 72 cell have a slight advantage in the rack cost. And for the tracker system, for the 1P tracker, due to the limited length of a tracker, so the 210 model will reduce the number of strings from 3 to 2 on 1P tracker. We can see in the left-hand figure for the 210 60 cell model, we can only use 2 strings and each string and 34 models, and the rack length is about 89 meters. And for the 182, we can use 3 strings, and each string have 28 models, and the track length is about 95 meters. So the total power of the 182 is higher than the 210, and which will save the cost per watt. And for the 2P tracker, is the same reason. The 210 model will have will have 3 strings, which is less than 102, and there is a string of models will be arranged on separate slides on the main axis, which related to the power loss due to obvious mismatch. And in terms of electrical equipment, in the left-hand side figure, we can see when the bifacial model working current increase, so the resistive cost will also increase, and the cable cost is will reduce. So if 4 square millimeters cable are used, that means the cost of 182 models is already under the optimal value. And if 210 models are using 6 square millimeters cable, and the overall cost will be equivalent to the 182 models. So there is no cost saving and for the 210 models due to the excess of time margin for the electric equipment. And we just did a simple both comparison example in the following figure, in following table. You can see both calculation is based on the same length of racker and installation cost, and there is slight advantage in 182 model due to the higher efficiency. In 3 plans, fixed both from fixed racker for landscape and fixed racker 2P and tracker 1P. So there is not obvious different both cost for all these 3 kind of conditions. The difference is almost 0.02 cents per watt. It's very slight. And also for the LCOE calculation, we made an assumption that the model price is same, and we can see from the obvious calculation the both cost of 210 model is 0.1 cents per watt higher, and since the 210 model have a higher current, that means the working temperature is about 1 degree higher than the 182. So we make the degradation all the same for CO2, 2%, and linear is 0.45%. We can get the 210 model will have a 0.5% higher LCOE than the 182 model. And lastly, I will introduce the HiPower 5 based on the smart soldering. So HiPower 5 is use the technology integration, which contains the M10 gallium doped mono wafer and high density packing segment ribbons, and use the reasonable 72C model design. For the smart soldering tech, in terms of the model efficiency, since the triangular section can maximize the use of sunlight, increasing motor power. And also we use the small gap technology. This is the best combination of high efficiency, reliability, and cost. So that means the motor efficiency will increase about 0.3% compared to the conventional MBB product. And I will also introduce this tech in details. So in terms of reliability, we did analysis on different process, for example, from soldering, laminating, and one thermal cycle. So all of these process showed that the tensile stress of the cells is 20% lower than the normal circular ribbon and the flat ribbon. So since smart soldering is integrated segment ribbon with small gap connection, and the ribbon is soft by annealing process, so the manufacturing yield is higher. We can see the smart soldering since using annealing process, so the lifetime is about 3 times higher than the circular shaping ribbon. And when we do the bending test, it will fracture about 20 times, after 20 times. And if we do the bending test for the circular shaping ribbon, so it will fracture up only after 7 times. So the main mechanism is that the smart soldering ribbon is very toughness. So the yield stress is about 60, I think it's 62 megapascal. And for the circular shaping ribbon, so the yield stress is about 70 megapascal. It's very brittle. And we did a verification of the lamination. After the laminate, so we can find there is no micro crack for the smart soldering technology. And for the circular shaping ribbon, we can find that a small micro crack will occur between the cell space. So the circular ribbon is locally flattened with higher internal stress, and it is easy to form micro crack after laminating. And we also did the dynamic and mechanical loading test for these 2 different technologies. And we can see for the smart soldering, we can see EL after test, we showed no micro crack of cells. However, for the circular shaping ribbon, we can find the micro crack of cell increase about 7 numbers. And also we did another threshold test of the test condition is about 5,400 Pascal mechanical loading plus 1,000 Pascal dynamic and mechanical loading and TC 50 cycles. We can find that the smart soldering showed less micro crack and degradation. The micro crack is only 2. However, for the circular shaping ribbon, the micro crack is 2. The number is too big, and the degradation is almost close to 5%. So therefore, the smart soldering is more reliable than the circular shaping ribbon. Basically, so conclusion. So from the M2 to M6 and to M10, increasing wafer and motor size has been an effective approach to increase motor power output and reduce both cost and LCOE. However, the size of P motor is not always the bigger the better. As I mentioned, we need to comprehensively consider all aspects of motor manufacturing process, as well as motor deployment process, transportation, installation, and long-term reliability, and to evaluate associated risk. So they consider your risk plan with the right table. 72 cell M10 based on the 182 millimeter cell is the optimal motor design for the large scale PV power plants after evaluating the whole value chain. And future efforts to lower LCOE will focus on the motor efficiency improvement to reduce both cost and improve the energy yield. So lastly, I will have a short preview about the SNEC, a new product. So For our new product, I think we are focused on the model efficiency. So the basic parameter, I think, will increase to almost 22% for the model efficiency. And also we will have a higher bifaciality and lower degradation and performance. That's all. Thank you.
Thanks, Jason, for this nice overview. Maybe a few questions. What about actually, of course, you're pitching for 182. The question is, what do you think is the optimal size in terms of length and width for a module?
Pardon me. What you mean? What kind of track length?
How long should be the optimal length and width for a module? I think someone asked in the from your perspective.
I think it's should below. I think it below 2.3 meters. Yeah, because we have communicated with many tracker suppliers. So most of the tracker is compatible with below 2.3 meters. If the model size is bigger than 2.3 meters, I mean for the 1P tracker, so it will increase the failure risk very significantly. It's not very mature now, so I think it's below 2.3 meters is a decent model size. Yeah.
That's for power plants. And what do you see for the residential C&I, or the more for rooftop systems? What would be the optimal sizes you see there?
Yeah, I think for the rooftop service, I think it's not. I think it's not mainly related to the motor size. It's most related to the motor weight. It's about a 20. It should be below, I think, 225 kilograms. So that means the motor length is below. I think is 2.1 meters. Is decent for the rooftop and the C&I. Yeah.
Okay. Maybe also a question. You said you refer. I think efficiency will be also one point at SNEC. I think there was one question. But what about actually regarding efficiency? What about you recently introduced a TOPCon new TOPCon cell record efficiency? Will we see soon a TOPCon module product from LONGi?
As you know, yeah, we have just I think released the TOPCon world record to about 25.09%. So it's world number one. Yeah, we're actually the new product in the SNEC. We use the new tech cells. I can not tell detailedly here, so maybe you guys can see our new product in the SNEC, and you will see what kind of new tech we will use for the new product.
Okay.
I only tell you that the model efficiency will increase significantly.
Okay. That's a nice hint. And I think that's it. Jason, if you have a few minutes left still, or even a little bit more, maybe take a look, please, at the chat, and if there are any questions, because I think there are some detailed questions, if you could answer them, that would be super nice. Huh?
All right, no problem.
Okay, thank you so much.